There we go. Okay. In our previous lesson, we looked at the fact that you get acids and you get bases, and when you titrate the two together, you have to choose a specific indicator. So remember that an indicator changes color depending on what solution you're in. Okay, so depending on whether it's in an acid or base. Technically, all indicators are to a certain degree, they themselves are acids or bases, and they either become protonated or deprotonated, fancy word for gaining and losing a proton. And as they do, they change color. In fact, if you've got a hydrangea outside in your garden, those big pom-pom flowers that are blue and pink and purple, those are also indicators. They change color depending on whether they're in an acid or a base. Even with lockdown and relatively limited supplies of a large number of things, I was able to still get hold of a red cabbage, which ironically enough is purple. And if you cut through a red cabbage itself, some of you may have seen this at school, is also an indicator. So what I wanted to just quickly discuss with you here, before I forget, is the 3 indicators that you are expected to know about and when you would use them. So this picture over here shows the pH versus the color of an indicator, the 3 specific indicators, and what colors they are at different pHs. So methyl orange, remember your low pHs here are going to correspond to acids, and your high pHs here are going to correspond to bases. Okay, and what you'll find is methyl orange is red in an acid and yellow in a base. One of the things that you'll notice is it changes color in around about the pH 3 to 4 range, which tells us that we use methyl orange when we titrate a strong acid and a weak base. And the reason is if you've got a strong acid and a weak base, you overall end up with an acidic salt, okay, or an acidic endpoint, okay? If you titrate or use bromothymol blue is blue in a base, got to write it in the right place, and yellow in an acid. It changes pH somewhere around about 7, so we technically call this a neutral endpoint. And when you have your neutral endpoint, you'd usually find that it's neutral because it comes from when you titrate a strong acid and a strong base, or a weak acid and a weak base. Okay, the last one here is phenolphthalein, which you'd use. So phenolphthalein in an acid is colorless. In a base, it turns a bright pink. In the example that I showed you on Tuesday, phenolphthalein was the indicator there in that video that I showed you. If you look at where its endpoint is here, it's going to have a basic endpoint. So it changes color when it's slightly more in the basic range, which is why you will always use it when you titrate a strong base and a weak acid. In an exam, they are allowed to give you indicators that are not on this list, but if they do, they'd have to add in information about what pH it changes color at to allow you to choose which indicator you should use. So this information here tells you when you'd use each of the different indicators, and the colors that they are given on this table along with the relevant pHs. So can I please suggest that you quickly take a snapshot of this? This is one of those things that you should memorize for an exam. It's not going to be a huge number of marks. It's 1 or 2 marks. Which indicator did you use and why? Or they give you a list of a few and they tell you what the pH is that they change color at, and you work from there. All right, so that was just to quickly bridge that little gap there and make sure that you're able to choose which indicator you're going to use in a specific titration. All right, so this was not at all the focus of what I wanted to do today. It was just me quickly tying up a loose end that I'd promised I'd tie up. All right, so what I'm going to do now is I'm going to quickly share my proper whiteboard, and we're going to quickly discuss what pH is and how pH works. So most of you for a relatively long time have known that acids and bases deal with things having pH. And pH, I've seen versions of it where it's the potential of hydrogen. I also at some point got the idea that in maths, P stands for negative log. And this is the negative log of the concentration when I was at school of just H plus. But recently we don't do just H plus. You guys don't deal with that. You deal with H3O plus. Because remember, as soon as you've got an H plus and water, they join together and make hydronium. So I'd like you to view at this point that pH is a measure of how acidic or basic a solution is. I had a thought while I was teaching on that previous slide, and it was just sometimes when you teach, you have little things that you leave off that you've later got to go back to and remember. I just quickly wanted to discuss one thing about bases versus alkalis. Some people get a little bit confused as to what the difference is between a base and an alkali. Please note that both bases and alkalis are things that will have pHs above 7, but the minor difference between them is that an alkali is a base that is soluble in water. Okay, so if I have something that's a base, it could either be a base or an alkali. If it's soluble in water, then we'll call it an alkali. But you could also call it a base, and more often than not, we don't differentiate between the two. The only time that we differentiate between a base and an alkali is when we're being a little bit nitpicky, and in an exam, they may ask you something about why can you say it's an alkali, and your answer is quite simply that it dissolves in water. If it can't dissolve in water, but it can accept protons, then we stop at calling it a base. If it can dissolve in water and can accept protons, you may either call it a base or an alkali. All right. So, sorry, I didn't mean to delete all of that, but I'll go back to it. The equation that you're always going to use to calculate pH is pH is equal to negative log concentration of H3O plus. Please remember, H3O plus is your hydronium ion. Okay, now if we give you a strong acid, it's actually really easy to work out the pH. So imagine I asked you to calculate the pH of a 0.15 mole per decimeter cubed solution of HNO3, nitric acid. So all that you've got to do is work out what the concentration of H3O plus is and write in your calculator negative log of that value, okay? This is where you've got to get smart about using your calculators, and you've got to realize that your log button is over there. If you've got a Casio, you may need to find it on your calculator if you've got something else. So in this case, I always recommend the following steps. It doesn't apply so much to this specific case, but I'm going to do it anyway. Write out your ionization equation. Remember, ionization is the reaction of your acid with water. And when this reacts with water, we're going to form H3O plus, okay, because that H joins with the H2O, and we're going to form NO3 minus. The whole reason that I did this is I wanted to show that one nitric acid produced one hydronium ion. So I can therefore assume that the concentration of HNO3 is 0.15 moles per decimeter cubed. And since it's 1-to-1, the concentration of H3O plus is also going to be 0.15 moles per decimeter cubed. The only reason that I could assume that those two would be the exact same value is because it's a strong acid, which means that it ionizes completely. Every single one of the HNO3s will break apart to form an NO3 minus and an H3O plus, guaranteed. From there, your calculation is you're going to say pH is equal to negative log of 0.15. Please remember, you only put the brackets in when it indicates concentration. You don't have to have that in square brackets. If you take your calculator and you write negative log 0.15 equals, I get a pH of 0.82, and that is my answer. So please remember, with an acid, your pH range is going to be anywhere from 0 up to, but not including 7. Now, just something to tell you with regards to this. It is possible using this calculation to get a pH that is lower than 0 and actually goes negative. We know this, okay? But we've said that the pH range that we do stops at 0, which means that when the person sets an exam, they're never going to make a pH that goes into negative range, but it is possible mathematically for you to get it. All right, so just be aware of that. Okay, so I think this is a relatively straightforward thing if you're dealing with a strong acid. Okay, now I want to do just one slightly harder one on this exact same question. So I'm going to quickly select and remove it and put in another strong acid here. And I'm going to do this with you because I don't want to catch you out, to calculate the pH of a 0.05 mole per decimeter cubed solution of H2SO4, also a strong acid. Now, this answer or this method is not going to be exactly the same as the previous one for the simple reason that H2SO4 is diprotic. It gives off 2 protons. So therefore, when I write out my ionization reaction, by the way, there are no marks for the ionization reaction. It's something that you do if you're smart and that you remember to put in yourself, is that this is diprotic. So it'll give off 2 protons, react with 2 waters to produce 2 H3O pluses and SO4 2 minus. That means that if the concentration of H2SO4 is 0.05 moles per decimeter cubed, that the concentration of H3O plus, it's a ratio of one of those gives us 2 of these, will be twice as much. Now, I find that you don't have to show your calculations. If you're good at maths and you don't mess up, I sometimes do, so I probably shouldn't speak on this, but if you don't mess up, you don't have to go and show that it's 0.05 times by 2 and how you got there. You can just assume that they can see you've done that step. In fact, you don't even have to show them that step. You can just jump straight in to pH is negative log of 0.1, and if you got the 0.1, they know how you got it. So it'll be negative log 0.1, and that gives us a pH of 1. Please note, if it is a strong acid, we usually expect a low pH. So we usually expect a pH somewhere around about 2 or less. It isn't an absolute rule, but it's where we should be. Okay, I just had a quick question and I'm going to follow up. Ma'am, isn't it +2 by the hydronium ion? No. Okay, the 2 goes in front here, and that says that there are 2 of those. I don't think that there's any other place where I could have had to put a hydronium. So the 2 plus goes, the 2 goes there and the plus goes there. All right, so I hope that everybody understands this idea of what you do when you're dealing with a strong acid. I am not going to go into great detail now with what you do when you deal with a weak acid, because weak acids actually come down to equilibrium calculations. So they are very unlikely to ever give you a weak acid, because if you get a weak acid, we've got to work out how much of this breaks up. And depending on how much of this breaks up, we'd be able to make an assumption about how much of this we produce. So it's not going to be a ratio which is guaranteed to be 1 to 2 if it is weak, and you need to actually be given what's called your Ka value in order to do that. So I'm going to quickly clear everything, and I'm just going to make a little note here that says For weak acids, since they do not ionize completely, you need to use your Ka value to calculate the concentration of H3O plus, and it gets very tricky. To give you an idea, I have not seen in the last, well, since they reintroduced this section, I haven't ever seen a question where they do a weak acid. But I'm pointing out to you that if they did, it would actually fall under the section of equilibrium, because we're dealing with a dissociation constant for acids. I'm, however, not going to waste time on that because the chances of it coming up are so slim that it isn't really worth our while doing it. Okay, it's going to be, if it ever pops in, it's your question to differentiate your 90 to 95% students. Okay, so it's really, really for the top kids. And I think that it's one of those things I'm aiming to do a broad thing here. It's possible if I find a question like that, I might go over it in the masterclass, but it's not something that everybody needs to know. All right, so that's just your own note for why we don't deal with weak acids. You're going to find the same thing for weak bases. We don't go there because it just gets messy. Now, when it comes to dealing with pH calculation for strong bases, we need to bring in some important facts. So the thing in order to use a pH calculation is pH is negative log concentration of H3O plus. But bases don't deal with H3O plus, bases deal with OH minus. Now, I am fully aware of the fact that there is a weird equation that uses the concentration of OH minus. However, it doesn't appear on your formula sheet, and therefore you will not get formula marks for using it. I am not going to teach it to you. What I am instead going to teach you, and please note this is me right now, strong bases is our heading, but I'm about to go off on a tangent. So everything that I say right now, in fact, I'm even going to just put it here, and I'm going to write this as an aside, or this is background information. Okay, so I'm going to go the background information, and then after I've discussed the background information, we're going to continue with strong bases there. So many of you may not know this, but there is a value called Kw, which is called the dissociation constant. I know that's spelled wrong. I hate that word. So it is the dissociation constant of water. And basically what happens is if you put water into any container, in fact, it doesn't even need to be in a container, if you've got water, the water will naturally break apart some of the molecules and produce OH minus and H3O plus. Okay, this is called the dissociation of water. And water automatically, very few molecules will randomly act as an acid and a base and give away a proton and accept a proton, and they do this all of the time. Now, we can work out an equilibrium for this because technically that's a liquid, and we can actually work out, I'm going to call it Kc now, but you're going to see I'm going to change that C just now. And I'm going to use a Kc, and I'm going to say, right, Kc is concentration of OH minus times by concentration of H3O plus. Those of you in grade 11, please don't panic. This is just how it works. So you don't have to understand the equilibrium just yet. Those of you in grade 12, you do. So it's a concentration of that times that divided by the concentration of water, but water is a liquid. So remember, we put in 1, which means that the equilibrium constant here is just going to be equal to the concentration of OH minus times by the concentration of H3O plus. And because it's for water, we use the symbol W, Kw, dissociation constant of water. So that's what it is. And just like any other equilibrium constant, we can determine what the value for this is at any specific temperature. And what we find is that this value is equal to 1 times 10 to the minus 14. Remember, equilibrium constants don't have a unit, provided we are at the temperature of 25 degrees Celsius. Now, for almost all of the questions you get asked on pH, we assume it's 25 degrees Celsius unless they tell us it isn't. So you can assume that you can always use this relationship unless they tell you that you can't. It's very rare that they try and sneak in a question where they change it without telling you that the temperature is different. If the temperature is different, we can actually have more dissociation, and therefore the ratio of these two can be above this value. If it's colder, it can be below the value, which actually means that by having a solution that's hotter or colder than 25 degrees Celsius, you can change something's pH, even though it's equally acidic or basic. All right, and the question here is, does this appear on the data sheet? Yes, it does. Okay, just give me 1 second. There we go. All right, so this does appear on the data sheet. In fact, I'll show you the data sheet in a second when we go to the examples I've got here. So when we deal with a strong base, what we're going to do always is we're going to work out the concentration of OH minus. We're going to plug it into this equation to get the concentration of H3O plus, and then we're going to take that value and plug it into the normal pH formula. I know that there is a shortcut, but I'm already telling you the shortcut isn't going to get you the marks, so please don't be tempted to use it. Now, one last thing before I later come back with the strong bases example, which will probably be on a new slide, is I want to talk to you about how we get a pH of 7 for neutral. So, if something is neutral, we can confidently say that the concentration of OH minus is equal to the concentration of H3O plus. Which means that if I have the concentration of OH minus times by the concentration of H3O plus equaling 1 times 10 to the negative 14, I can safely say that the concentration of H3O plus times by the concentration of H3O plus is 1 times 10 to the minus 14. All that I did here was I said, well, if this is equal to this, then this is this guy, and it must be equal to that too. Okay, so those are all equal, so I can stick that in there. Therefore, I can say that the concentration of H3O plus must be the square root of this. So if I square root both sides, I get an answer of 1 times 10 to the negative 7. And therefore, the pH will be negative log of 1 times 10 to the negative 7. And I challenge you all, stick that in your calculator right now, and you get a pH equal to 7. Please note, if the temperature is higher, the neutral pH is actually above 7. So our always assumption that pH of 7 is neutral actually only exists at 25 degrees Celsius. If you make the solution hotter, according to Le Chatelier's principle, more of it could dissociate, and you could actually end up with a neutral pH having a slightly higher value. Just a sneaky thing to do there. Okay. Can everybody quickly take a screenshot of anything that they need? Because I'm going to clear this. Okay. So what you'll therefore find is that if we've got a neutral situation, our concentration of H3O plus equals our concentration of OH minus, and therefore the pH is determined to be 7. If we've got something that's acidic, then our concentration of H3O plus will be more than 1 times 10 to the negative 7, and therefore our pH will be less than 7. You can try it, plug in any value, and you'll see that it works. And if we have something that's basic or alkaline, our concentration of H3O plus will be smaller than the concentration of OH minus, and therefore it will be smaller than 1 times 10 to the negative 7, which gives us a pH that is more than 7. All right, before I go any further, I'm just going to quickly ask you to take your screenshot of this, and before we move on to how to actually do the strong bases, I wanted to quickly ask, who already knew what I've just covered on why you get your pHs of 7, below 7, and above 7? Thumbs up if you already knew it. Okay, seems to be one of those things that they often don't test. So if I'm looking through here, I'd say that probably 1/10 of you knew it, I'm very glad to see some of the people that I've taught know it. That's a good sign. Sometimes I think as teachers, we forget what we teach and what we don't teach. All right, so let's carry on with this. So that is how we end up with all of the different pHs. Okay, so I'm going to clear this and we're now going to deal with an example of a base. And you'll see bases are harder to work with than acids. Acids, you took it and you plug it in. Bases, you've got 2 steps. So your question here could be to calculate the pH of a 0.15 mole per decimeter cubed solution of KOH, potassium hydroxide. Now, once again, you're not going to get any marks for this, but if you don't do the first step and you get it wrong, you're going to have a problem. So I say KOH will break apart to give me K plus, which is aqueous, and OH minus. I do this so that I can see what my ratio is of KOH to OH minus. Please, this is only once again for strong bases. It's the only way that you can assume that this is a ratio of 1 to 1. So from that, and I'm not going to write both of them down. Actually, maybe I will. Sorry, habits. KOH is 0.15 mole per decimeter cubed. And therefore, the concentration of OH minus is also 0.15 moles per decimeter cubed. So from there, I'm not certain if there's a question there. Please ask if there is. I can go and jump straight in with the concentration of OH minus times by the concentration of H3O plus equaling 1 times 10 to the minus 14. You do not need to write the KW part of this equation. You can jump straight into this bit. So here I know that 0.15 multiplied by the concentration of H3O plus is 1 times 10 to the minus 14. So therefore my concentration of H3O plus is going to be 1 times 10 to the minus 14 divided by 0.15, which gives me a messy answer of 6,67 times 10 to the negative 14. I'm going to leave that in my calculator so that I don't round up. Then I remember that pH is negative log concentration of H3O plus, which will be negative log of 6,67 times 10 to the negative 14. I'm sticking with the full value in my calculator. So I'll write negative log, I don't know if it'll allow me to write just the answer. I'm going to have to double check this one. I got an answer of 13,176, but I don't know if that's because it remembered the previous answer. So I'm just going to double check. And it appears to be close enough. All right, so that'll be your pH. pH usually given to 2 decimal places, but yeah, I wouldn't round up more than that. Okay, so with your bases, you need to remember that there are 2 formulas which are essential. If you do not have this formula and this formula, you're not getting all of your formula marks. All right, okay. When would the concentrations not be equal when you have a strong base? I'll do a second example right now to just quickly cover that eventuality. So can everybody quickly take a screenshot if you wanted to of this? I'm going to do just one more calculation with you, and then we're going to move on to examples that I put aside where I'm going to quickly give you a chance to do them. Then I'm going to check the answer, and you can see whether you understand them. There are a few, but we're going to start with easy and then go to harder and harder depending on how time goes. All right, so I'm going to quickly clear all the drawings. So the example of where it isn't necessarily going to work out is if I have, for example, calcium hydroxide. And I tell you that the concentration of calcium hydroxide, remember square brackets is concentration, is 0.05 moles per decimeter cubed. And I ask you to calculate the pH. Please, this is very shorthand, but you can figure out what I'm doing. So I ask you to calculate the pH. What you would then do is you'd have to show that calcium hydroxide would dissociate to give you calcium and 2 OH, sorry, that's Ca2 plus, and 2 OH minuses. And therefore, we'd say that the concentration of OH minus will be twice as much because it's 1 to 2 for our ratios. So the concentration of hydroxide would be twice as much, so it'll be 0.1 mole per decimeter cubed. From there, what you'd do is you'd remember that the concentration of hydroxide multiplied by the concentration of hydronium. I must be honest, you can write these either way around in an exam. Nobody's going to freak out. So if you can't remember which one goes first and you're a little bit lazy and you don't want to look at your formula sheet, you will get the marks as long as it is correctly done with square brackets. Okay, now there's a question here that says, ma'am, when we were at school, we learned an easier method where you find POH and then subtract from 14. Please, I understand exactly what you're talking about. That's the method that I told you that you're not likely to get your formula marks on. So please, I'm going to caution you against it. If it's not on the formula sheet, they don't have to give you the marks. So there is a chance that the examiner will be lenient and will give you full marks for it because you do get the same answer, but you're not technically using the same steps. So I'm teaching you the official method. If your teachers taught you another method and they're prepared to mark it, that's fantastic. I hope for your sake that the examiners will also mark it correctly. But if it isn't on the formula sheet, I'm not prepared to say that it'll get marked one way or the other. I haven't been involved in marking acids and bases, and I must be honest, I've never really worried too much about that method and whether you get the marks or not, because I deliberately don't teach my students it. All right, so if you know it, if it works for you, and if you're prepared to take the risk, I'm not going to stop you. I am fully aware of how it works. When I was at school, I was taught a similar method, but I wouldn't recommend it. All right, so over here we got 0.1 times by the concentration of H3O plus goes to give you 1 times 10 to the minus 14, and therefore our concentration of H3O plus is going to be 1 times 10 to the minus 14. I don't know why I'm doing this on my calculator, divided by 0.1, give me 1 times 10 to the negative 13. I'm going to blame it for being late in the day. And your pH is negative log concentration of H3O plus, which is negative log of 1 times 10 to the negative 13, don't lose my value. So if I put that in, I'm going to get a pH of 13 units. All right. Just one last thing on calculating pH. When you get to the answer, just check that it's reasonable. Go back and say to yourself, wait a second, this was a base. Is this a pH that's for a base? Is it on the right side? Because sometimes what you do is you lose your mind for just a second and you substitute this value straight into here. And then you get a pH that's below 7 and you don't have that checking moment where you go, wait a second, this is a base, what's going on? So please do yourself a favor and make sure that you do double check it against this. All right, I'm going to quickly clear here. I hope everybody's good with that. We've got about 25 minutes, and I want to see how many of the questions I've put together that we can get through. Got about 5 of them, so I'm hoping we can get through all of them. All right, so I'm going to quickly change what I'm sharing. I'm going to do a new share. I'm going to share my screen. Brilliant. Okay, so carrying on this document over here, we're starting with past paper questions. Now, these questions are not for a huge number of marks, but they came out of a real exam paper, like a proper matric exam paper. So these are all DBE proper matric exam papers. This, just for the record, is a quick screenshot that I took of your formula sheet. So you can see over here, I've just included concentration as number of moles of volume, just in case you need that bit of it. This is for titrations, which is not what I'm focusing on. So the 2 formulas that you're going to be using are that one and this one. I tend to use that portion of it, but if you want in an exam, you can stick in the KW value as well. All right, so this would be worth 4 marks in an exam. And the question is to calculate the pH of a 0.5 mole per decimeter cube sodium hydroxide solution. Now, bearing in mind that both formulas are there, and I'm giving you a big heads up, sodium hydroxide is a base. So you're going to use both of them. I'm going to stop sharing on my screen right now. I'm going to ask all of you to quickly grab a piece of paper and try and work this out for yourself. If you're at home, I know many of you prefer not to do actual working while we're doing these, but I promise you it'll make more sense to you and you'll remember it better if you've managed to try and do the questions yourself while we're going through them. All right, so I'm going to work it out while you're working it out, and when I'm done, I'll then check how many of you are already done. Okay, go for it. And remember, when you get to the end, that you double check that the answer that you get is appropriate for a strong base. So it should be somewhere between 12 and 14 usually. Please note I'm saying usually because you can end up with a very dilute strong base that isn't quite that high, but it's very irregular. Okay, can I ask if you're already done with it? If you can give me a thumbs up. Okay, good, that looks promising. Okay, look like majority of you, and unfortunately, because we do have a little bit of a limit on time, I am going to push you just a little bit to get to the answer, because I think if I wait for everybody, we may not actually get there. So I'm going to quickly share what I did. So here's my full working out. Read the blue before you read the black. So what I did was I said that sodium hydroxide dissociated to give us 1-to-1 with hydroxide. So therefore the concentration of the hydroxide was also 0.5. I put in the formula, I did my substitution, I got to my answer. Please, just so you're aware of where your marks are, and if we're particularly lenient with this being 4 marks, sometimes we merge those two equations for 1 mark. Sometimes we give them a mark each. Usually there will be a mark for this substitution, and there will be a mark for this substitution, and then there'll be a mark for the final answer. All right, can I quickly ask who got that correct? Thumbs up if you got it right. Okay, good. All right, fantastic. Some of you are making me laugh. All right, I'm going to quickly clear all of these, and then we're going to scroll down. Okay, so that was the first question, which was sodium hydroxide. Just so you know, when I put together these questions, I came across similar ones for sodium hydroxide a number of times, each just with a different value. So the sodium hydroxide for 4 marks, I'm not going to say it's often, but it's often enough that when I looked through about 4 papers, I got it. All right, the next question over here is a little bit unrealistic. And the reason I say it's unrealistic is that it says ethanoic acid is an acid that ionizes incompletely. Actually, I lie, I read completely. It is a realistic example. So it ionizes incompletely in water, which means that we're dealing with an example here where we actually have a weak acid. Okay, so this is giving you an example of how they can bring in a weak acid if they do. When I said this, I didn't realize that's what it was, but hey, we'll go with it. Okay, so there's the equation, and you must remember that since this is weak, we cannot assume that our concentration of hydronium is going to be 1:1. So the first question says, write down the term used for the underlined phrase above, which is an acid that ionizes incompletely in water. My gosh, I'm bad at this game. It is a weak acid. I find quite often when I don't read the questions, I jump straight to what the answer is before I remember. All right, question 7.1.2 says an ethanoic acid solution has a pH of 4 at 25 degrees. So this is a little bit backwards. We're giving you the pH, and we're asking you to calculate the concentration of hydronium ions. Now, as confusing as this seems, this is actually just us giving the same question and working backwards. So I want to quickly ask, who knows how to work backwards from pH? So where you're given a pH and you're asked to work out a concentration. Thumbs up if you know how to work backwards. Okay, slightly fewer of you than I'd like. So I think out of fairness to everybody, because this is a backwards question, I'm not going to make you do it on your own just yet. If you want to, you're welcome to mute me and not look up just for a little bit, and then you can check that you can do it on your own. All right. So I'm going to work here, and I'm going to say, well, pH is equal to negative log concentration of H3O plus. I then plug in that 4 is my pH, is negative log of concentration of H3O plus. So the first thing I do is move the negative across. So negative 4 is equal to log of concentration H3O plus. Now, most of you in maths should already have done logs, but basically on your calculator, you're going to end up doing 10 to the power of. So you're going to look at where your log button is on your calculator, and you're instead going to push shift log, which if you look at it should give you a value of 10 to the power of. Then you're going to put in your pH, which is negative 4, and that will give you a concentration of H3O plus. You do not need to write this step in. I'm just following from what I'm doing here. If I write shift or second function log of negative 4, my calculator says 10 to the negative 4, which is what I'm working out. And if I push equals and then push my surds to decimal button, I get that the concentration of H3O plus is 1 times 10 to the negative 4. Now, up till now with pH, you may have noticed I don't put in units because pH is unitless, all right? But when we're dealing with this question, the question is asking you to work out the concentration, which means that your answer isn't unitless. Your answer is going to be concentration, and I shouldn't be writing down concentration. I should instead be writing down moles per decimeter cubed. All right, so that's just something that we could do here that's a little bit backwards. Because we were dealing with an acid, we jumped straight into the pH calculation, and we didn't have to go around in little circles. All right, I'm hoping that everybody understood this question. I'm just quickly going to ask, did everybody understand this question? If you didn't, please speak up quickly, because this is one of the ways we can ask. These all came from past papers. They're all realistic. They're probably a little bit easier than you're going to get in an exam paper, but I want to start you off relatively easy. Yes, Divine? Divine, is that a question? Yes?
No, ma'am, excuse me.
Okay, don't worry. Mute yourself, that's fine. Okay. All right, so next question. Okay, now here we hit a relatively long question. So this we're going to take a little bit of time over, and I actually want to see if you can work your way through it. Okay, the big hint that this is for quite a large number of marks tells you it's likely to be a tricky question. So I have a sneaky suspicion, looking at the fact we've got 14 minutes left in the lesson, I'm willing to bet that between this and answering the questions that come from it, this may be one of the last questions we get to. So you were told that a sulfuric acid solution is prepared by dissolving 7.35 grams of sulfuric acid liquid. That tells you that it is 100% pure. So you can assume that you can use the molar mass of H2SO4 and the mass to work out the number of moles of sulfuric acid in 500 centimeters cubed of water, giving you a heads up here. Don't forget to convert it to decimeters cubed. Sorry, there shouldn't be a negative. It isn't per decimeter cubed. It's just decimeters cubed. All right. So the first question that everybody can quickly do, I'm going to stop sharing while I do it, is to calculate the number of moles of sulfuric acid present in the solution prepared. Please, the question is the number of moles, not the concentration. Okay, so I'm going to quickly pause. Go for it. One of the equations that you use is right over here. And just in case you don't know it, the molar masses of hydrogen is 1, I should write that there. Sulfur is 32, and oxygen is 16. You should look those up on the periodic table, but I'll save you some time. Okay, thumbs up if you got an answer. Okay, good. Anyone who doesn't know, when I say thumbs up, you can actually click on reactions at the bottom of your page and there's a thumbs up symbol that it gives it. I don't mind if you give me a proper thumbs up if you've got a camera showing. It's just so you know if you don't have one. All right, so I'm going to quickly jump to my answer. You should have found that the molar mass was 98 grams per mole. So here, your mass of 7.35 divided by your molar mass should give you 0.075 moles. All right. You were then told that sodium hydroxide pellets. Now, when we say pellets, sodium hydroxide is literally sold as little pellets, and they are roughly, I don't know, about that size in diameter. So half a centimeter to a centimeter in diameter, and they're little half round domes. They look a little bit like chocolate chips. Okay, so they're literally that shape and size. There's something about that big, sometimes smaller. So those little pellets are added to the solution over here. The balanced equation for the reaction is given over there, and you are told that after completion of the reaction, the pH of the solution was found to be 1.3, and we can assume that H2SO4 has complete ionization. That means that it is a strong acid, which we should assume, but I think they put it in because sometimes people get fussed about whether it is or isn't. Now, the question that we've got is to calculate the mass of sodium hydroxide, which was added to the H2SO4 solution, and assume that the volume of the solution does not change. Whew. Now, this is quite a large amount of work. It's going to be quite a big challenge for quite a large number of you. So I want to just quickly run you through which steps I would do in order to solve this. I'm sure that some of you already have an idea as to how to do this, but I'm going to tell you what I would do. So the first thing that I would do is I'd start with the 1.3, and I would use the 1.3 pH to calculate the concentration of H3O+. The reason I say specifically H3O+ is that this is in the acidic range. Okay, so if I know the final pH, I can know the final or the end or the, we can even call it excess, H3O+. Now, the reason I say excess is that some of the acid will be neutralized by the base. But the fact that overall it's acidic tells me that we have got more sulfuric acid than sodium hydroxide. I'm going to calculate the H3O plus excess. The second thing that I'm going to do is that I'm going to calculate the number of moles of H3O plus in excess. And the way that I'm going to do that is I'm going to take this value and I'm going to use the equation concentration is number of moles over volume. I know the volume because it's given over there, and we were told that the volume of the solution does not change. Okay, so this is my steps for going backwards. So I'm going to calculate the concentration of H3O plus in excess, and I'm going to calculate the number of moles in excess. Now, I already know the number of moles initial. This 0,075 is the number of moles of H2SO4 initial. You should know, okay, with regards to these, that if this is the number of moles of H2SO4 initial, I can work out from this the number of moles of H3O plus initial. Okay, because if I consider what happens with H2SO4, it will ionize or react with water. It's diprotic, so 2 of them to form 2 H3O plus and an SO4 2 minus. So I can know that if this is this value with moles, then the initial amount of H3O plus, which was produced by the complete ionization, will be twice as much. So I know that I actually start with 0,15 moles. So if I know how much I had initial and I know how much I had at the end, I can know how much I had that reacted with my sodium hydroxide. Okay, so I'm then going to say that the number of moles of H3O plus that reacted will equal the number of moles of H3O plus initial minus the number of H3O plus that were in excess. Okay, so basically if we've worked out this value and we take this and minus whatever we get in number 2, we'll be able to work out the number of moles of H3O plus that react. From that, we can work out the number of moles of OH minus that react as well. Because even though they do give you, it is possible, by the way, to do this from these 2 values and to work out H2O and then go into bases. So you can do H2SO4 and NaOH. You can stay with those 2 instead of going to H3O plus and OH minus, but I prefer, since they're dealing with pH, to go straight into OH minus and H3O plus. So I can work out the number of moles of OH minus that react, because I can go and look at the ratio here, okay? Or I can even go that OH minus reacts with H3O plus to produce water. There are other ways to do this. Once I know the number of moles of OH minus that react, I can use that to work out the number of moles of NaOH. And once I've worked out the number of moles of NaOH, I can use that to work out the mass of sodium hydroxide. All right. Now, what I've just described to you is the thought process that goes through my head when I get a question like this. Is how am I going to link all of the parts together? When you get more experienced at doing these, quite often you just start and you kind of start and you go, well, I've got the pH, I'm going to do this, 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 and then you build up all of the pieces. But sometimes it's useful to have somebody guide you through what all of the steps are that you do here. Now, part of the problem with a question like this is that you unfortunately cannot learn these steps off by heart, because in the next question we change it just slightly and suddenly the sequence of steps don't follow the same pattern. So with something like this, it's actually really helpful to practice lots and get the idea of how to do it. All right. I want to just quickly have a look. I'm going to quickly open up so that I can see everybody that's still here. I wanted to ask, who would like me to go through how to calculate the answer to this question? because it's going to take a little bit over time. A thumbs up if you're prepared to stay till the end, and I'll go through the whole working out with you, because I think that this is where a lot of you tend to fall apart a little bit. So just because we are ending towards the end of time, I'm going to give you an option right now if you want to take a screenshot, and then you're welcome to go and practice this and try it on your own. But I'm going to spend our time now going through all of the steps. Now you're going to have to bear with me because there's quite a lot, there's little space and lots to do. So what I'm going to do here is I'm going to take all of this away because I don't need this. What I do need here for me to remember and to work from this is that I do need to write in here a couple of notes for myself, like that this value was 0,075 and that the initial number of H3O plus was 0,15. Okay, and then I'm going to work through the whole solution right now. Oh, that doesn't have units there. Okay. All right, I can see a question. Which year is this paper from? I must be honest, I can't tell you. I think it was from one of the 2016 papers, but it's not an unusual question. So as much as it's a tricky question, you're going to find that a large number of acids and bases questions are like this or worse. There's often going to be a nasty pH question. Probably one in every 4 papers has got something similar to this. All right, so I'm going to get started with each of my steps. Step number 1 was to use the pH of 1.3 to calculate the concentration of H3O+. I must write that pH is negative log concentration of H3O+. So from there, I'm going to put in 1.3 is negative log concentration of H3O+. And then I'm going to remember that this becomes negative log. Please remember it becomes negative log. I'm jumping straight to the answer because I want to make sure we save a bit of time. So if I write log of negative second function log of negative 1.3, I get an answer here that the concentration is 0,05011. I'm keeping all of my decimal places so that I don't lose them. So that over there was what I said I'd do as step number 1, okay? And that's the excess. That's what we don't use. So therefore, step number 2 was to calculate the number of moles. Well, number of moles of H3O plus in excess is going to be concentration multiplied by volume. That's just me rearranging that equation, which is going to give me 0,05. I'm going to carry on with the full values on my calculator though, and this is going to be multiplied by 0.5. So I get an answer. I know I'm being a bit of a hypocrite because this has got ... values and I'm not writing them all in, but this is 0,025 and then it's going to be 0.6 moles. Okay, so up to the end of step 2. Now I need to work out the number of moles of H3O plus that react. So I'm going to go back and say, well, we started with 0,15 moles from the mole ratio that we did here, where I did that example and I showed you that it was diprotic. So it's going to be 0,05 minus 0,02506. So I'm going to subtract those two, and I get the number of moles is 0,12494. I know I'm keeping lots of decimals, but that's okay. And that tells me my number of moles of H3O plus that react. Now I could, I guess, work out and even jump across. Maybe it's easier rather than us going into the hydroxide and I'm suddenly looking at it and going, maybe I should just change this back into H2SO4. Because the number of moles of H3O plus that react, well, each sulfuric acid gives me 2. So I can work backwards at this stage. So maybe it might be easier and slightly less confusing for some of you if instead of me working in hydroxides, I jumped straight at this point to sulfuric acid. So I think I'm going to do that just to make it easy. But remember, each sulfuric acid produces 2 H3O pluses. So I must divide this number by 2 to work out that this concentration is 0.06247 moles. Does everybody understand that? That's just the mole ratio that each of these dissociates to give me 2 hydroniums. Okay. From here, I now have the number that actually reacted. So I can go and replace this with the fact that the number of moles of H2SO4 that actually reacted was 0.06247. Okay. And therefore, I can say that the number of moles of sodium hydroxide, it's going to be a ratio of 1 to 2. So therefore, it's going to be twice as much. So I can say this times by 2. I know it feels like we're going backwards, but it's going to be 0.12494 moles. Okay, that actually is a lot easier than what I was doing earlier. This step over here was unnecessarily complicated. I could just have jumped straight in. So what I ended up doing here actually was, I'm just quickly correcting it, that I went and worked out the number of moles of H2SO4 that react. Then I worked out the number of moles of NOH that react. These two depend on this mole ratio here. And then lastly, I worked out the mass of sodium hydroxide. So to work out the mass is equal to the number of moles multiplied by the molar mass. Rearranging that equation, the number of moles is 0.12494. The molar mass is going to be 40 grams per mole. Sodium's 23, oxygen's 16, hydrogen's 1, which gives me an overall value of 40. So if I times that by 40, I get a mass of 4,997, which is the same as 5 grams. You may round it up at that point. All right. Can I please suggest that you take a photograph of this or a screenshot of this if you need to? Because I'm going to clear it in just a second. All right. Are there any questions on this? Does everybody that stayed till the end make sufficient sense of how I've gone about solving this? And most importantly, probably, how you go from the concentration of H3O plus and the number of H3O plus to the number of moles that react, and then how you link all of that back into the question. All right, great.
I'm sorry.
Yes, Jackie.
Do you think you could explain how you go from H3O plus to H2SO4? I know you divide it by 2.
Okay.
Is that because?
That was because of the step that I wrote up at the top of the screen just a little bit earlier, where I said H2SO4 will react with water, 2 waters in fact, to produce 2 H3O pluses and an SO4 2 minus. Okay, so it's the idea that each one of these produces 2 hydroniums. So each sulfuric acid molecule produces 2 hydronium ions. So therefore, if I know that I have got, where's my value? If I know that I have got 0.12494 of these are in a ratio of 2 parts to 1 part, then I must take this, divide it by 2 to get 1 part, and times it. So this, from here to here, we had to divide by 2. It's just using this mole ratio, and bearing in mind that if we've got that number of moles, we divide by 2 to get what 1 is in the mole ratio, and then times it through. Did that answer your question?
Yes, thank you.
Okay, brilliant. Any other questions? Will the H2SO4 keep dissociating in spite of the sodium hydroxide? Well, the thing is that dissociation doesn't really depend on what else is happening around it. I always use the example, I teach at a boys' school, so I always use the example of dissociating as you come with your parents to watch rugby, you get out of the car, and my gosh, do you go in opposite directions? Like it's literally, they split apart, and for the entire day while watching the same rugby at the same school, they're completely separated. What they're doing individually, the parents interacting and the children interacting, has no impact on the fact that the second they got out the car, they split apart. So the dissociation happens before any subsequent reaction. It's what allows us to take, well, in this case, I've actually got to correct you on your wording. H2SO4 ionizes, it doesn't dissociate. So our H2SO4 will ionize regardless of what's later going to happen with the sodium hydroxide that the H3O plus will react with it. It would react whether it is or isn't there. And we don't usually consider things like Le Chatelier's principle or other things where what later happens to the particles will affect whether more is made or less is made. This isn't a reversible reaction specifically where we're looking at factors like that. It's testing us on acids and bases. All right, I'm going to quickly clear my screen. Oh, wait, no, I'm not. I'm going to check the last question. All right, that was just a thank you. Whew. All right, sorry, let me get out of my screen. There we go. All right, ladies and gentlemen, thank you very much. I hope that that made good sense to you. And please remember to keep practicing on Siavula. The masterclass has so far been a rather big hit, but we have the same group of 30 people there every week. So I'd really love you to give it a bit of a shake up and to work for your place there as well. All right. Have a lovely evening.